Okay, so first of all, does anyone have any questions about the vector review or any of the problems I assigned? Okay. Um, then we're just going to keep going with the mathematical preliminaries. Um, so remember that what we're doing, let's see, I didn't bring the sheet that said, but so we did derivatives of vectors. With one caveat that until Monday you didn't know you even had to worry about. What's that? We did derivatives of vectors under what conditions? Yep. Perfect. Yep. Um, and now we're going to do the product rule. Um, and the chain rule for vectors. And then we're going to do one class of differential equations. So we're going to do solving ODEs. What does ODE stand for? Well, we're going to do separable equations, yeah, but the ODEs thing stands for ordinary differential equations, which means one independent variable. So we're not doing partial differential equations using separation of variables. Okay, so the first one we're going to do, we talked about the derivatives last time. This thing has so many annoying little. Okay, we did this one. So we're going on to product rule for vectors. Oh, man, what a crazy time. But I need to say something about doors. I mean, it's been so, always like, a door is locked and you prop it open and, it helps people get in and whatever. But doors have to be latched pretty much now. If the doors are latched, uh, officers can't legally open the door without a judicial warrant. So we need to keep doors latched. If they're held open with a door stop or whatever, that's an open door and anybody is allowed to go in. Okay, so it's insane. Yeah, no shit. Um, okay, so product rule for vectors. So product rule for scalars. Let's talk about that. So if you're taking like d whatever, it doesn't matter what the variable is. Let's say s of some function or variable f times some function or variable g. So the way you do this is df ds times g plus f times dg ds. And just So you've seen that a million times, maybe not in exactly that form, I don't know. But so that's how you do the product rule. But I want to point out one thing that with scalars in your whole life up until now, it's been equally true that you could think of this as df ds times g plus dg ds times f. There's no problem with that at all, right? But in order for this to just directly translate over to vectors, don't think of it this way. Get in the habit of keeping that order the same. And then you just don't have to do any extra thinking with vectors. Do you know what I mean? So this is correct, but think about it this way. Okay, keep the order of those variables the same. And the reason for that is that when you're multiplying vectors, there are multiple ways to multiply vectors. One is the cross product, and the cross product order matters. Okay, so like a vector f times a vector crossed with a vector g is not the same thing as the vector g crossed with the vector f. And so that's why you want to keep these in the same order. And I'll show you. I don't know. I'm talking sort of in abstract right now, but I'll show you what I mean. Okay, so what are the ways you can multiply a vector? So the first one is multiplying a vector by a scalar. And I'm going to write these. All of these are true derivatives for any variables. I'm going to do it with the variable being t because that's pretty much going to be our independent variable always in dynamics. So if you're taking d dt of a scalar a times a vector u, that is dA dt times u plus a times du dt. And because of the definition of the dot derivative operator, we can write this as a dot times the vector u plus a times the vector u dot. And so for the rest of them, I'm just going to keep using the dot because it's more compact, you know. But remember that definition of the dot operator. The next one is the product rule when you have the dot product of two vectors. So if you're taking the time derivative of the dot product of a vector u with a vector v, this is u dot dotted with v plus u dotted with v dot. Okay. And let's think about the dimensions, because in order to take the dot product between two vectors, they need to have the same length. They have to have the same number of components. So when you take the time derivative of this vector u, say that it has three components, then the time derivative also has three components, and you can compute this dot product. Then in the next term, when you take the time derivative of the vector v, it has three components, and you can take that dot product too. Okay. And then the last one is the cross product. This is the one that we have to be careful about because order matters in the cross product. So if we're taking the time derivative of u crossed with v, bless you, this is equal to u dot crossed with v plus u crossed with v dot. And this is the one that's the reason why you want to keep the order of those variables the same when you think about what the product rule is. Because this one is not equal to u dot cross v plus v dot cross u.
Wouldn't it be equal to u dot cross v minus?
That's true, but you can imagine why you don't want to. I mean, you want your brain space is precious. You want it to be as clean as possible, and that is throwing garbage in the corner of your brain space. Okay. Okay, anybody have any questions about those? Now we'll talk about the chain rule. This is number 3, I guess, in my list. So the chain rule says ddt of a vector function. So let's say that this f is a vector, but it's a function of a scalar independent variable. So let's say it's a function of g, which is a function of t. Well, the chain rule says that this is equal to the derivative of f with respect to g times dg dt. Or you could also write that as derivative of f with respect to g times g dot. And there's really one specific way that this is going to come up often in dynamics. So this will arise in dynamics often like this. So we know that the acceleration as a function of time is defined as the time derivative of the velocity. That relationship is never wrong, okay? And we'll also see a similar relationship between the angular acceleration.
That be v dot t?
Yes, thank you. Thank you. And the angular acceleration as a function of time is defined as the time derivative of the angular velocity. But so if you have the velocity vector as a function of time, or you have the angular velocity as a function of time, then getting to the acceleration and angular acceleration, those are easy, right? You just take the time derivative. But what if you don't have, what if you have those as functions, but they're not functions of time. And we'll see that come up some, a good bit. But what if you're given the velocity vector or the angular velocity vector as functions of a position variable instead? So, like, for example, what if you know that the velocity, say you're given the velocity vector as a function of y, the height or something. Okay. Can you think of any cases from physics 1 where you would have been able to calculate the velocity of something as a function of the height? The height is kind of a giveaway on this. Yep. Yeah, so anytime you're using conservation of mechanical energy, you're coming up with a relationship between position variables and speed, velocity. You can turn it into velocity. But now what do you do? First of all, why do we always act like we care so much about acceleration? What's so special about acceleration?
It's the change of velocity over time.
That is the relationship, but there are going to be a lot of cases where we are given something about velocity and we want to know what the acceleration is. Like, what's so special about acceleration? Yeah.
Because that's what the force is dependent on.
Yes, exactly. So I think of it like this, when you're downtown and it's cold outside and you want to get from this building to this building. Let's say you're on the first floor over here and you want to get to the first floor over here, Well, it's cold. It'd be nice if you could just go first floor to first floor, but there's no way to do that because the Skyway is on the third floor or whatever. So in order to get from this building to this building, you have to go to the Skyway, And acceleration is the Skyway between loads and motions. Okay, so no matter what you want to do once you get from motions to loads, the way to get there is always going to be through acceleration and through angular acceleration. Okay. That's the Skyway. Yep.
So then, so in order to convert from potential energy to mechanical energy, right? It has to go through acceleration.
Yeah.
Okay.
Right. So what do we do if we have a case like this? Well, so what we're going to do in this case is we're going to say the acceleration vector is equal to the derivative with respect to time of the velocity vector. So that's the definition. We know this is true. But now we can use the chain rule here and say that this is equal to dv dy times dy dt and dy dt is just the y component of the velocity. Right? That's part of that definition. And so this is just equal to dv dy times the y component of the velocity. I just chose y kind of arbitrarily. You can do this with x and z also. But what we have here now is we've calculated the acceleration as a function of y without ever knowing what t was. But don't make the mistake of, here's the easiest mistake to make, thinking acceleration is the derivative of velocity. Okay? Acceleration isn't the derivative of velocity. Acceleration is the derivative with respect to a very specific thing, time, not anything else, you know? So if you look at this and say, I'm just going to take the derivative of the velocity with respect to y, and that'll give me the acceleration, your answer will be wrong. Okay, it's only with respect to time, but we can use this chain rule idea. Okay, so let me do an example of that. This isn't something you really have to know yet. We'll spend more time on it later, but let's say that we're given that the velocity vector is a function of y, and that function is negative 2y, y, negative y squared. Okay, like due to some crazy energy field, potential energy field, force field. If you know the height, this gives you the velocity vector at the height. And we want to calculate the acceleration as a function of that height. Okay, we want to do that because then we can use Newton's laws to go to forces and everything. Okay, so how are we going to do this? So the acceleration is equal to dv dy times dy dt. And dv dy is negative 2, 1, negative 2y. And dy dt is the y component of the velocity, which is y. So this is negative 2, positive 1, negative 2y times y. And now the acceleration as a function of y is equal to negative 2y, positive y, negative 2y squared. Okay, so we're going to use that all the time. Okay, and then the last preliminary math topic is solving ODEs. I'll write it out, ordinary differential equations. ODEs. Using separation of variables. Okay, so in order to solve any differential equation of any type, partial, ordinary, whatever technique you're using, you have to be able to identify what the dependent variables are and what the independent variables are. The dependent variable or variables are the functions you're trying to find. And the independent variables are the variable, well, this is only going to be one for us, you know, because we're doing ordinary. So the independent variable is the variable derivatives are being taken with respect to.
So the independent variable is the dependent variable. The independent variable is the variable the dependent variable
Yeah.
depends on.
That's right. So we're always trying to find, so solving a differential equation, solving an ordinary differential equation means finding, that is not how you spell finding, means finding the dependent variable as a function of the independent variable. For ODEs, you only have one independent variable, but you can have multiple dependent variables. With partial differential equations, you also can have multiple dependent variables, but you also have multiple independent variables. Okay, so like for us, the independent variable is almost always time. So we're trying to find other things as functions of time. Often those will be like position components, you know? Okay, so let me just write something out. And so let's say that you have the differential equation, second derivative of y with respect to time plus 10 times the first derivative of y with respect to time is equal to 10y squared. Okay. What does it mean to solve this ordinary differential equation?
Find y as a function of t.
Yeah, exactly. So solving a differential equation is always about finding a function of the independent variable. So in this case, we want to find y as a function of time. And if you can find that function, you know, cosine times sine divided by 4 or whatever, like you come up with that function, then you've solved that differential equation. So this is what our job is going to be, because we're always going to have ordinary differential equations. Okay, so when can you use separation of variables?
When there's no when y and t aren't in the same.
Okay, so here's the rule. If you can set up a differential equation in this form, where you have, and I'm just using random letters for my variables, but if you can set it up into the form where you have a derivative of one variable with respect to the other is equal to a function of, well, based on this derivative, what's our dependent variable? Our dependent is f, okay? Our independent is q, because we're taking the derivative with respect to q. And if you can set it up as where that derivative is equal to a function of only f things times a function of only q things, then you can get all the f things on one side, all the q things on the other side.
Doesn't it usually involve the answer a logarithm?
I mean, we'll see how that, can come up pretty naturally, but I don't know if I would say usually. Yep.
Would it work if you didn't have the HQ? Could you still do it?
Oh, yeah. Yes, for sure. And then, right. I mean, you can, because then you can just think of that function as one. It's still a function. It's just a lame function, It's just really boring. But then you just get a longer coffee break. So the way you solve this is you got df over this function g of f is equal to h of q times dq. And now you can see those sort of naturally lend themselves to taking integrals, so you can integrate both sides and come up with an expression. One thing that is important for doing these is, so anytime you integrate something, you get a constant of integration. So notice that this integration, well, really you would get two constants of integration because you're integrating two things. But since they're both arbitrary, you can just add them together and call it a single C, So this integration produces an unknown constant of integration C and we're going to find C through boundary conditions. In math, I think when you talk about differential equations, you're usually concerned with a general solution, meaning that that your constants C are sort of built into it. In engineering, you're going to tend to be using boundary conditions to find kind of like a specific function solution to your differential equation. So every time we use separation of variables, we're going to have a boundary condition that we can then use to calculate that constant of integration. Yes?
For example, we might know that at the beginning of the test, the tank has 10 gallons of water.
Exactly. Yep. So, okay, so let's do an example. So let's say that our differential equation is y dot is equal to y squared t squared. Where y at time equals 0 is equal to 10. So this is our boundary condition. This y dot, the definition of that is dy dt. And now I'm going to move all the y things over to the left and all the t things over to the right. So we have dy times y to the minus 2 is equal to t squared dt. And now we'll integrate both sides. So we have negative y is equal to t cubed over 3 plus, I'll put the combined constant of integration over on that side. It doesn't really matter. Oh, whoops. That's to the minus 1 power. And I'm just going to apply this boundary condition, I'm just going to use it in the form that I got here. I mean, I could right now get it into a function form, but let's just use this. So now I'm going to use the boundary condition, which says I'm going to plug in 0 for anywhere t is, and I'm going to plug in 10 for anywhere y is. Anyone have any questions about what I'm doing there? So we have negative 10 to the minus 1 is equal to 0 plus c. And so, bless you, that says that c is equal to negative, my computer needs a break every like 40 minutes. It's very lazy. So this negative 10 to the negative 1 is negative 0.1. And now I can plug that into this expression. Well, maybe I'll do it all as fractions. So I'll write this as negative 1 over 10. And now I'm going to update my function now that I know what c is, or update my relationship. So we have negative y to the negative 1 is equal to t cubed over 3 minus 1/10. So we have negative 1 over y is equal to 10t cubed minus 3 divided by 30.
So now it's just algebra to get.
Yeah, that's right. Now it's just algebra, but you do want to, for solving these, like on a test or whatever, you'd get the vast majority of the points if you came up with this expression. But really what you'd like is to get the dependent variable written as a function of the independent variable. So, I'll do the algebra, and we get that y as a function of time is equal to 3, nope, got to flip them. So 30 over 3 minus 10t cubed. Yes?
When we get constant answers like C in this case, is there a preference in this class what form we should put it in, like scientific notation, decimal, or fraction?
Oh no, there's no preference. Yeah. I also am very very loose with significant figures. You don't have to worry about any of that stuff.
So,
Your chemistry teachers will make you worry about that so much. I feel like I can ignore it.
yeah, so in this class, we don't have to worry about like rounding anything or.
Yeah, you can round as much as you want. I'm just going to follow the steps that you follow. If you want to call pi 3, that's fine with me.
Okay.
If you want to call it 1 times 10 to the 0, that's fine with me.
Oh, and do you want us to write y of t every time?
No, I don't really care. I just want to be able to follow your steps, Right now, I'm trying to be real explicit with everything just to make sure that we're kind of on the same page at the early going. But okay, so now this is what you're going to see more often in this class, just because of the kind of stuff that we're going to do. And at first, this might not look like a separable thing, obviously, but that's what this really is. So let's say that we know that we have So let's say this is just a 1D motion. So like a motion along a line. And let's say that the velocity is equal to 3t squared plus 5t minus 10. And at time equals 0, x is equal to 3. So this is our boundary condition. We're going to use that to find the constant of integration.
And we're always going to be keeping these like boundary conditions.
You'll always get them, yeah. Yep. So, okay. First, we have to figure out how this is a differential equation at all. So we're going to use the definition that says v is equal to dx dt. You know, that's a definitional relationship. And so I'm going to rewrite this as dx dt is equal to 3t squared plus 5t minus 10. And then you can think of this as, you can think of this times 1. So this is our function of t in the first set of parentheses multiplied by our function of x in the other one, And now we'll separate them, get all the x stuff on one side, that's just dx. Get all the t stuff on the other side. So 3t squared plus 5t minus 10 all times dt. And now we can integrate both of these. So dx is equal to t cubed plus 2.5t squared minus 10t plus our constant of integration c.
There's the x here, right?
Yeah. Yep. Now we'll use the boundary condition to find that c. So the boundary condition says I'm going to plug 0 in for all the t's. I'm going to plug 3 in for all the x's. So we have 3 is equal to 0 cubed plus 2.5 times 0 squared minus 10 times 0 plus c. And so c is equal to 3. And so then we'll update our function. And you get x as a function of time is equal to t cubed plus 2.5 t squared minus 10t plus 3. Okay. Well, what if you have higher derivatives? Because we won't really care about anything higher than second derivatives in this class, but we'll see a lot of second derivatives. So what about higher derivatives? So let's say that we have an acceleration that's equal to 0, negative 9.810. And we're given that the velocity vector let's choose a more interesting time. So let's say the velocity vector at time equals 1 is equal to 1, 5, 1. And let's say that the position vector at time 2 is equal to -6, 0, 10. Okay, well, this is an ordinary differential equation. Well, let's set it up, I guess, just sort of a step at a time. So let's say that we're going to say that the acceleration is the derivative of the velocity with respect to time. And that is equal to 0, -9.81, 0. And for this step, the boundary condition that's going to matter is that the velocity at time 1 is equal to 151. And so I'm going to break this up. Like really what this is 3 different ordinary differential equations. So you can think of this as like dv dvx dt is equal to 0, given that vx at 1 is equal to 1. Separate variables, you get dvx integral is equal to the integral of 0. And so this just says that dvx is equal to c. No, I didn't do this again. Vx. And now we'll use the boundary condition that says set Vx equal to 1 when you set time equal to 1. And so 1 is equal to c. And so, c is equal to 1. Update your function. And we get that Vx is equal to 1. So there's our function. Why don't you take a couple minutes and see if you can do this for the y equation, and feel free to talk to people next to you. Feel free to ask me questions if you get stuck, but this is just making sure that you're sort of following along. So now we're going to do dvy dt is equal to -9.81, given that when time is equal to 1, v is equal to 5. So vy at time equals 1 is equal to 5. So we're starting with this dvy dt equals -9.81. Separate variables, and you get dvy is equal to -9.81 dt. And now you can integrate both sides, and you get vy is equal to -9.81 t plus c. Sometimes you need to be careful about this kind of stuff. This c is not the same as this c, but I'm just sort of, since I'm doing it one step at a time, I'm just like reusing that variable name. So now we have our function. This function is correct. We just don't know what C is. So we'll use the boundary condition for that. And the boundary condition says when t is equal to 1, vy is equal to 5. So plug those in and you get 5 is equal to negative 9.81 times 1 plus c. And so c is equal to 14.81. And now we'll update. And you get that Vy as a function of time is equal to negative 9.81 t plus 14.81. Anybody have any questions about that one? Okay, I'll just do the last one quick. So now we have that dvz dt is equal to, that was 0. And the relevant boundary condition is that when time is equal to 1, the velocity is equal to 1. So we have Vz is equal to C, use the boundary condition, and it says that 1 is equal to C. And so the final function, Vz, as a function of time, is equal to 1. Okay, so now what we have is we have an expression for the velocity vector as a function of time. And that is, the first one was 1. The second one was negative 9.81 t plus 14.81. And the third one was 1. And now if we're going to calculate the position function, now we have to do another step. So the next step is to find the position vector as a function of time. Well, we know that this is the velocity function, and we can write that as, so the velocity as a function of time is defined as the time derivative of the position. So we can say that dp dt is equal to this thing. Yep, do it again. Now things are a little more, there's more going on. We won't have the zeros and stuff, but, and we have the boundary condition now, the one that's relevant is the one up here that says at time equals 2, the position vector is negative 6, 0, 10. So when the position vector, when the time is 2, this is 6, 0, was it positive 10?
Yes.
Okay.
I think it was a negative 6 as well.
This, negative 6?
Yeah, negative 6, 0, 10.
Okay, thank you. And we're going to do it just step by step. So why don't you take a second and see if you can do the x component of this differential equation? So if I separate these variables, we get dx is equal to dt. We can integrate both of those. And we get that x is equal to t plus some constant. So there's our function. Then we'll use the boundary condition that says plug in 2 for t, you get -6 for x. So -6 is equal to 2 plus c. So c is equal to -8. And now we just update our function. And we get that x as a function of time is equal to t minus 8. And now the next one, now we go to the y equation. So that says dy dt is equal to this expression for the y component of the velocity. So -9.81 t plus 14.81. And our boundary condition here says at time 2, y is equal to 0. So let me give you a fake amount of time to do this problem again. And then pull the rug out from under you before you have a chance to finish. So I got dy is equal to the quantity -9.81 t plus 14.81 times dt. Integrate both of these, and you get y is equal to, this is -4.905, adding significant figures at random, times t squared plus 14.81 t plus c. And now we'll apply our boundary condition, which says we'll plug 0 in for y when we plug 2 in for t. So 0 is equal to -4.905 times 2 squared plus 14.81 times 2 plus c. 19.8, I think that,
9.62 should be the first one.
yeah, and then negative, and then this one is positive 29 point.
When I did it in the calculator, T was 10.
C was,
-10. C was -10.
C is -10. C equals -10. And so now we update. And we get the y as a function of t is equal to -4.905 t squared plus 14.81 t minus 10. And then I'll just do the third one. So we have dz dt is equal to, I already forgot it, 1 is equal to 1, where z at time equals 2 is equal to 10. And so dz is equal to dt. So z is equal to t plus c. And now the boundary condition says 10 is equal to 2 plus c. So c is equal to 8. And so z, as a function of time, is equal to t plus 8. And all of this together tells us that the position vector is equal to t minus 8 negative 4.905 t squared plus 14.81 t minus 10, and then t plus 8. And so that is our position vector. One thing I want you to notice is in order to solve, you need one boundary condition per dependent variable for each integration level that you take. So you need one boundary condition for each dependent variable at each integration step. And actually, I should say, to be real careful, instead of saying at each integration step, I should say for each integration step. Because in fact, I could have given you this problem, and there's an assignment problem that I'll give you where you have to do this. Instead of saying the velocity at some time is this and the position is this, I could have said the position at one instant is this and the position at another instant is this, and you could solve it still. Okay, anybody have any questions about that? That was an example of an ordinary differential equation, not just where we did two levels of integration, but also where we had multiple dependent variables. And in dynamics, that's kind of how the multiple dependent variables will show up. They'll show up as components of vectors. Okay, that's all for today. That's more than enough.